All right, so it's time for us to get going. So we're going to start by reminding ourselves that we have this game plan in place. And we've talked about it before. In fact, this is pretty much the same thing that we've had before. And so how does the game plan work? Well, it says, suppose that you have x prime equals ax. A is a matrix. Let's say it's an n by n matrix. And I want to solve it. So the procedure is fairly straightforward. It says, well, step one, find the eigenvalues of A. And you're guaranteed you will always succeed. There's always going to be n eigenvalues. And these come from solving for roots of the characteristic polynomial. So we can find those. Step two says, okay, find, if you can, in other words, if it's possible, n linearly independent eigenvectors. And once you've found those, you can make solutions by e to the eigenvalue t times eigenvector. So in some sense we said, okay, this is great. It all comes down to finding these things called eigenvalues, eigenvectors, and life is good. But now we come back to the if possible. And that's a note. Not all matrices have a full set of eigenvectors. You can encounter matrices that are short. They don't have all that you need. And, well, in that case we need to bump. And that's what we're talking about today. So how do we handle it when we don't have all the eigenvectors that we need? All right. So let's just start with an example. Find all the eigenvalues and eigenvectors for this matrix. 5, 4, minus 1, 1. All right. Well, where do we start? Okay, so one thing is you always need to find your eigenvalues before you can find your eigenvectors. You can't find eigenvectors unless you have the eigenvalues. So we start with that characteristic polynomial, lambda I minus a. And remember that these bars here mean taking determinant. So we're taking the determinant of this matrix. All right. So that's the determinant of lambda minus 5 minus 4 plus 1 lambda minus 1. So lambda I means you put lambdas on the diagonal, and then you subtract a. Well, okay, 2 by 2 matrix, that's not too bad. So you multiply down the diagonal. So that'd be lambda minus 5 times lambda minus 1. And then subtract, multiplying on the other diagonal. So subtract minus 4. All right. Now what? All right, so the suggestion is expand. So we expand. So lambda times lambda, lambda squared. There's a minus lambda, minus 5 lambda, minus 6 lambda, and then there's a plus 5, plus 4 more, which makes it plus 9. Now remember, when we take this determinant, what are we going to do with it? We're setting it equal to 0. So we're finding when does the determinant equal 0. All right, so lambda squared minus 6 lambda plus 9 equals 0. Well, when is that true? Someone said 3. When else is it true? 3. Yeah, we already said 3. But when else is it true? Oh, the other 3. That's right. It's the other 3. So yeah, this actually factors as lambda minus 3 squared. So in other words, we actually have 3 is an eigenvalue twice. And it's okay to have eigenvalues repeat. So, all right. So our eigenvalues are 3 and 3. All right. Great. We're halfway done because it said find eigenvalues and find eigenvectors. Well, we found eigenvalues. So the next thing is let's find eigenvectors. All right. Well, that means we're looking for some vector where lambda I minus a times our vector. I'll call it xy for the time being. equals, what should I have over here? So if this is an eigenvector, lambda I minus a times the eigenvector should produce what? Zeros. If you think about what this says, if you distribute this, it'll be lambda times the vector and a times the vector. And they should be the same. That's what an eigenvector does. So we actually know what lambda I minus a looks like. It's come up here, but now put lambda as 3. So we're really saying minus 2, minus 4, and 1, 2 times xy needs to be 0, 0. All right. So what do we have here? We'll write something like this down. What is this? It's a system of equations. Right, it's a system of equations. Good. And so we have to solve it. Now, there's lots of ways to solve systems of equations. I'm going to go through and do things like the augmented matrix just because it'll be useful later on in an example. But that's not the only way you can do it. So we have minus 2, minus 4, 1, 2. And on the other side, we want to get zeros out. Now, we've talked about finding eigenvectors before. You can go as far as you want, but really, in some sense, don't feel bad if you say, oh, I've just gone far enough. And far enough should be like, have I simplified to a very reasonable extent. Now, for 2 by 2, what should always, always, always happen is if you've done your eigenvalue computation correctly, is that you should see that these 2 rows should be multiples of each other. And if these 2 rows are multiples of each other, what should happen? You can knock a row out. If they're multiples of each other, you can automatically knock a row out. And so which row do you want to knock out? Yeah, let's just knock the top one out. Now, you can do the computation and you can just say, that knocks out. So you say, okay, great. That's knocked out. Boom, gone. And now you're down to one single row. You say, all right, well, what is this row? And if you think about what this means in terms of our variables x, y, the first column is x, second column is y. So in other words, as you read down through here, top down to bottom, it's the same as going from left to right along there. So the first equation being knocked out says we don't need to worry about that anymore. And the second equation says, hey, we need x plus 2y equals 0. And we're just looking for any solution that where this works. Well, not any solution. There's one solution we're not going to use. 0, 0 is a bad choice. Why is 0, 0 a bad choice? I mean, it's true, but why is it bad? Well, okay. What is it we're looking for? Eigenvectors. What must be true about eigenvectors? They're non-zero. So I can't pick 0, 0 because then I end up with 0. I have to find something non-zero. So can anybody spot a solution to this? Any solution will work. As long as it's not 0, 0. Negative 2 and 1. All right. So if we choose x equals negative 2 and y equals 1, then we have our nice vector negative 2, 1. Now, you might say, well, that's an eigenvector, Steve. Are you sure that there's not more? You've already circled it as though this was the right answer. To which I respond, that's a square. That's not a circle. But good question. Okay. So how do we know there's not more? Well, if you look at this equation, you can say, hey, this is the same as x equals minus 2y. That equation. So that says that our solution, xy, has to look like minus 2y, y, or it's some multiple of minus 2, 1. So any solution looks like minus 2, 1 after you've appropriately scaled it. So it is our only answer. Remember one thing we've said before. Eigenvectors aren't unique because you can multiply them. And if I haven't said it before, I'll say it now. If I double an eigenvector, it's still an eigenvector. If I quadruple it, it's still an eigenvector. So we can always scale. On a side note, if you are faced with a situation where you're trying to find, say, I don't know, an eigenvector of a 2 by 2 matrix, just repeat the process, right? You set up your lambda I minus a, you get to knock out a row for free, and you get down to, let me just put a little box here. And you say, well, there's some relationship ax plus by equals 0. And sometimes you can spot spot a choice for x and y very simple, and sometimes it's like, But here's an easy choice that will always work. Choose x equals minus b and y equals plus a. And what happens? You get minus ab plus ab. So they will cancel out. And so if you get down to that one equation, the coefficients will help you say, aha, I know what my eigenvector is. And so finding eigenvectors for 2 by 2 should be pretty quick and automatic. So in other words, it's something we shouldn't stress about too much. Okay, so this is an example where we have a shortfall. We don't have enough eigenvectors. Now you might notice that the eigenvalue was repeated. That's not a coincidence. Every eigenvalue always has at least one. So if your eigenvalues are distinct, you'll never have a shortfall. You'll always succeed in finding eigenvectors. So the only time this could happen is if you have repeated eigenvalues. But even when you have repeated eigenvalues, it can still be the case that you still might be able to find enough eigenvectors. It just depends on the situation. Okay, so we still haven't answered the question, how do we bump? So here we go. So talking about, say, a 2 by 2, doesn't really matter. But we have lambda is repeated eigenvalues. And there's only one eigenvector for lambda. Like, okay, great. Well, once you have an eigenvalue-eigenvector pair, there's our eigenvector, there's our eigenvalue, you have a solution. So we know e to the lambda t times v is a solution. Great, we know that. What's our second solution? We say, all right, well, we think back to what we did before, back before we had systems. We said, well, before we would just take our answer and we bumped up by multiplying by t. We said, hey, look at us, we can multiply by t. We said, okay, well, let's try that. And this is not a bad way to approach things. You say, okay, let's try something and see if it works. Now, the majority of times that you try something, you'll fail, and we will fail. But it's what we'll learn in our failure which will help us. So our first guess is, hey, multiply by t. Well, there's some problems. One thing is if you compute the Wronskian, it'll be always 0. That's bad. We don't want a 0 Wronskian. But there's an even bigger problem. So we're trying to work with this x prime equals ax. That's our key. We say, well, let's check. X prime. Well, t e to lambda t, what rule do we need to take the derivative? Product rule. Now, the v acts like a constant because it's a constant. It doesn't change at all. It's always v. So what's the derivative of t times e to the lambda t? There'll be an e to the lambda t and also a lambda t e to the lambda t. So this e to the lambda t is if you take the derivative of t. This lambda t e to the lambda t is if you take the derivative of e to the lambda t. All right. On the other hand, a times x, well, the t e to the lambda t acts like a constant, so that just comes out. And a times v is lambda v, because it's an eigenvector. And now we do our classic sort of, cross your eyes and lay them on top of each other and get like a 3D equation. But you'll notice something. it doesn't line up. These parts match. That's good. We like things to match. But this part can't hook up to anything. There's nothing for it to match with. So the problem is, the reason why just multiplying by t is not enough is there's this little extra piece here. And we say, okay, so we have to somehow account for that. And we say, well, we're not going to just start from scratch. We say, well, let's just modify our answer. See, this is what you do. You try something. It doesn't work, we say, okay, let's modify it to try to get a better answer. What's our modification? We say, well, we need a little bit extra. And so what we'll do is we'll add an e to the lambda t times w. Well, what's w? Well, we're going to figure that out. So w is something. We're going to see, is there some w where this would work? So let's see what we would need. So we're checking. All right, we want x prime equals ax, so you take x prime. Now, we know how to take the derivative of the first part. That's what we did before. And then the derivative of e to the lambda t times w, well, the lambda comes down, e to the lambda t times w. On the second part, well, we have ax. We know how to take a times the first part, but then we say, okay, what's a times w? And the answer to what is a times w is? Yeah, a times w. Because we don't know anything more. We don't know what w is yet. And now we say, okay, here's the thing. In order for this to do what we want it to do, this part on the back, these pieces have to match up. Because we already see that the first parts match up, no problem. And so we have our great, let's stare at this for a while. What do all these things have in common? E to the lambda t. Since they have it all in common, what can we do? Yeah, get rid of it. So what we really need is that the v plus lambda times w needs to equal a times w. As long as that was true, we would be good to go. So the next thing is we say, all right, let's clean it up a little bit, and we'll join things together that should be together. In particular, there are two things with w. So we put them together. AW minus lambda w. So we brought that to the other side, and that should equal v. All right, great. Now, let's pull a w out. Well, there's a little subtlety which we've handled before. We can't just straight pull a w out. We need to add a little bit in here so it makes sense. But like we've done before, add an I and you're fine to go. So we need a minus lambda I times w to equal v. All right. So here's the great aha. So if this is true, so in other words, if we can find such a w, then here's our new solution. And here's the great news. We can find w. It's guaranteed to work. That doesn't even look like the word can. We can find w. So now we've said, okay, it's not just a matter of straight up multiplying by t. There's a little bit of an error correction term that you have to add in. And that error correction term relates back to the a minus lambda I. Okay, so that's what's going on. Well, let's try an example. Find the general form for solutions of x prime, which is 5, 4, minus 1, 1, x. All right, now we're doing differential equations. Good. We're cooking with gas here. All right, well, does this matrix look familiar? Yeah. Where did we see it? Yeah, the last problem. We say, hey, let's just pull up for reference here. We've got the eigenvalues, we've got the eigenvector. And we say, cool. So this is one of those cases where we're short a little bit. So we have to actually go through and do our bumping. So our eigenvector, and we're going to call this v, is minus 2, 1. Okay. So we still have a solution already. So this e to lambda t times v is a solution. So we're like, great job, us. Good. So x1, which would be e to the 3t, because lambda is 3, times minus 2, 1. Now x2, well, will be, according to this, t e to the 3t times v, so times the same vector, plus e to the 3t times something. We'll have to fill that in. All right. So, our work is what goes in the box. As they ask, what's in the box? What's in the box? Okay, well, we're going to figure that out. Be patient, be patient. Okay, so let's start by looking at this. We need a minus lambda I times w, which I'll call w1, w2, is equal to v, which, well, is minus 2, 1. So we know A is the matrix. We know lambda is 3. So we can say A minus lambda I is 2, 4, minus 1, minus 2, times w1, w2, and we want that to be minus 2, 1. Okay, so what do we have here? We have a system of equations. It should feel very deja vu-y. It's like, ooh, kind of feels very similar to the kind of system we did before. The difference is, it's not zeros on this side. Okay, well, that's all right. We can still go through the same process. So 2, 4, minus 1, minus 2, and minus 2, 1. All right, what can we do? Okay, can we? How? I believe you when you say we can eliminate a row. How do we eliminate a row?
Can we multiply the bottom by 2 and then add it to the top?
We can multiply the bottom by 2 and add it to the top. That's a great idea. Okay. So if we do this, the bottom, well, stays the same. The top, 0, 0, 0. Okay. Now, the top row of all zeros, that's a good sign. Bottom row, minus 1, minus 2, 1. We can read that off as an equation. What equation is it?
Negative x minus 2y is 1.
Almost, yeah. Instead of xy, we're using w1 and w2. But yeah, minus w1 minus 2w2 equals 1. All right. So the vector we're looking for, w, satisfies this relationship. Now you might be saying, wow, but there are so many things that satisfy this relationship. Which one do we pick? And the answer is choose simple. Okay, that's the mantra. So do you have choices for W1, W2 where this is true? Think simple. Easy as you can possibly go. Well, negative 1, 0 is good. Okay, so someone said negative 1, 0, and someone I think said negative 3 and 1. Now, which one of these will work? Trick question. Both will work. Like, whoa, they both work? We'll get why in just a second. All right, so which one do you want? Doesn't? Yeah, negative 1, 0. Like I said, they both work, so just pick. Okay, so now we have our x2. All right, now, are we done with the problem? No, but we're really close. If we're after general form, what's our answer look like? Some constant times the first function plus some constant times the second function. Now you could put this together if you wanted to, but you can leave them separated as they are here. And that is the answer. Now it doesn't have to be A and B. You could use C1, C2, whatever you want to use. All right. Very quickly here, short discussion. Why doesn't it matter? Well, let's just ask the question, how do these two differ? So let's do a subtraction, if you will. So let's suppose we take this vector, minus 3, 1, subtract that vector. Minus 3 minus minus 1, what do you get? Negative 2. 1 subtract 0, what do you get? 1. Where have you seen this before? It's our eigenvector. So this is our eigenvector. It's like, what? So here is a quick note, and I'm not going to leave this on the screen for very long. I know people like to write things down. But I'll scan it in so you can just copy it later. But it says, look, your choice for W is not unique. However, any other choice differs by a multiple of your eigenvector. Now, why does that say, hey, it doesn't matter? Well, if I replace W by adding a multiple of V, what we can do is we can move this part into the first piece. So it becomes some A plus B times this multiple, e to the lambda TV plus this other part. And then I say, oh, well, this is just a bigger constant, so it becomes a new constant. So what's the moral? It says, hey, it doesn't matter which W you pick. There's lots of them. Keep it simple. So don't think about, I have to find the right W. Think of it as like, I want to find an easy W for me to work with. All right. Good. So now we know. Now we know. But you might say, well, that's pretty easy, Steve. What if we have something harder? Oh, you had to ask. All right. So the first paragraph looks intimidating, but it's just terminology. What the first paragraph says is we call our eigenvalues complete if we have a lot of eigenvectors. In other words, if we have an eigenvalue repeated k times, there are k different eigenvectors. We say, great, we love that eigenvalue, it's complete. You complete me. If there's an eigenvalue which has less than what we want, we say it's defective. Now you might say, well, wait, can we ever have more? No. No, you can never have more. You gotta have either the full amount or less. Okay, so complete just says there's nothing fancy you have to do, no bumping involved. Defective says, oops, you got a bump. Now, there's one case where you can bump and it's not too much hard work. Hard work being a relative term. And that is, suppose you have an eigenvalue and there's only one eigenvector. So that's the setting. You have, eigenvalue might be repeated many times, but there's only one eigenvector. And in that case, what we can do is we can create a series of functions where we work our way up. So the first function is the one we already know about. It's e to the eigenvalue t times the eigenvector. And we know this is an eigenvector because a minus lambda I times v1 equals 0. That's what it means to be an eigenvector. Now, the next one is what we just talked about. E to the lambda t, tv1, so we went up from v1 to tv1 plus v2. A minus lambda I v2 equals v1. Now, here is where things get a little bit like, oh, so that's what we've been doing. Look at the next one, x3. You have e to the lambda t. So here, you might think, oh, we should have t squared, but we don't. There's like a little piece here, 1 over 2 factorial. What? tv2, add a new vector. And again, where the new vector is sort of, we're working our way up. See, every time it's a minus lambda I times the new vector equals the previous vector. Look at the next one. We instead of 1 over this thing t squared, it's 1 over 3 this thing t cubed. What's actually happening here? Well, it's kind of like telephone, but what does it look like we're doing here? If you see t, this is t. By the way, what does this 2 exclamation mark mean? It's not like, oh, I'm so excited, I get to do something in the equation, yay! That's not what the 2 is doing. What does the 2 exclamation mean? Factorial. It means like 2. 3 factorial means 3 times 2 times 1, 6. So what we're really doing is it looks like we're integrating. And the reason we're integrating is secretly so that when we check the answer, the derivatives match up. Because when we take derivatives, we don't want to have these powers coming down and like throwing a wrench into our plans. Anyways, the point is this process will continue. And we'll be able to succeed in finding k functions. And the fun thing is, if you try to keep going, it breaks down. It says, no, you can only find k when you try to find k plus 1. Forget it. Hopeless. It's not happening here. Okay, so I want to, again, go through why this works. And so I'm going to really quickly look at this part right here. So x3. Why does this work? Now, if you take a look at these equations, there's something we should point out. We got this by merging the sides together, but we could really say, hey, this says a times v3 is really 2 things. It's lambda v3 plus v2. This previous equation says, hey, a v2, it's really lambda v2 plus v1. And this last one says, hey, a v1 is really lambda v1 plus 0. And I want to point this out because it says that, hey, when you multiply by a, you're doing 2 things. You're sort of scaling that vector by lambda, but you're also adding the previous vector. And that's going to show up here. Okay, so again, I apologize. As a reminder, this will be scanned in. So let's suppose we want to check x3. So I copied x3 here. All right. So to check x3 says I look at x3 prime and I compare it to ax3. So x3 prime is product rule. So we can take the derivative of e to the lambda t. That's not so hard. Leave the other part alone. Or we take e to the lambda t and take the derivative of the other part. And this is why we like the factorials downstairs, because the derivative of t squared over 2 is t and not 2t. ax3, well, all right. I multiply everything by a, distribute through. So there's an av1, an av2, and an av3. So I can do what I just had on the previous slide. So av1 is lambda v1, av2, v1 plus lambda v2, and av3 is v2 plus lambda v3. And what you should see is like, oh, it's like we're getting 2 things from every term. Well, if you think of product rule, you really are getting like 2 pieces from each part. And now we are going to do a quick matching game and say, do things line up? So the last part here is I just expanded. And we say, okay, well, let's see. The lambda e to the t, 1/2 t squared v1, well, that's right there. If I have the t vt, and that's with the lambda, that's right there. And then if the v3, that's right there. And for the last piece, well, the t v1, e to the lambda t, that shows up right there. And the v2, e to the lambda t, shows up right there. So the way I think about it, it doesn't have to be the way you think about it. You may not want to think about it, but I like to say, in essence, what's happening is because of the way we choose the AV2 to really become 2 pieces, that's capturing how the product rule has 2 parts. And so that's how it works. Okay, so great. Now, a word of warning. This works great and all if we have just 1 eigenvector. If you have 2 or more, hopeless. Well, not completely hopeless, but it gets very complicated. Now the reason it gets complicated, you might say, well, wait, doesn't the process work? And the answer is it does work if you start with the right vector at the beginning. You're like, okay, Steve, well, that doesn't sound so hard. If I have two eigenvectors, doesn't that give me a 50-50 chance of being right? What do you think? If I have two eigenvectors, that just means two candidates, right? And the answer is no. If you have two eigenvectors, so that says I'm in space and I say, okay, there's a vector here, and maybe there's a vector there. Those are eigenvectors. Well, those aren't the only eigenvectors you can get. Because what you can do is you can combine them in various ways. You can take linear combinations. And so what you actually have is you don't have two eigenvectors, you have a whole range of eigenvectors. Each point here on this plane would be an eigenvector. And you might say, okay, so that's fine. I have infinitely many possibilities. How many give me my answer? Well, you have to be just right. So you have an infinity to 1 odds that you get it right. So that's bad. Now that's if you start at the bottom and work your way up. So if you only have one eigenvector, then you know where to start. So no problem. But if you have two or more, it's hopeless. You don't know where to start. In that case, if you have two or more, you start at the top and you work your way down. There's an example in the book, but we won't do that in this class. But if you want to know more, of course, there's always more math to learn. And the key is looking at what happens with these a minus lambda I to a power. Okay, so in our remaining time, I hope we can get an example. Find the general form for solutions of x prime is 5 minus 1, 1, 1, 3, 0, minus 3, 2, 1, x. And there's a nice hint for us. Oh, they like us. Hint, for the matrix we have that lambda I minus a equals lambda minus 3 cubed. Okay, so what is this telling us? Yeah. And what are our eigenvalues? 3, 3, 3. Good. Good. So that's great. So now we're going to be looking at this matrix A minus lambda I. This is going to be an important matrix for us, so we'll go ahead and compute that. So it's the same matrix here, just subtract 3 off the diagonals. So lambda is 3, that's why we 3, and I says only worry about the diagonals. So that would be 2 minus 1, 1, 1, 0, 0, minus 3, 2, minus 2. So this matrix is our key matrix. All right, first step is, let's find out if it has any eigenvectors. So let's suppose I'm multiplying it by, I'll call it u's, u1, u2, u3, and I want to get out 0, 0, 0. In other words, this is an eigenvector. Well, we have a system of equations. So 2 minus 1, 1, 1, 0, 0, minus 3, 2, minus 2, 0, 0, 0. What can we do? Yes?
If we subtract the second row from the third row, then the third row becomes a multiple of the first row.
Okay, that's one thing. How about we do this really quickly? This 1, 0, 0, 0. Oh, I like that row. That's a really good looking row to me. Like that's a cool row. I'm going to multiply that by 3 and just knock out entries and multiply by negative. So multiply by 3, add down. Multiply by negative 2, add up. And we'd get 0, minus 1, 1, 0, 1, 0, 0, 0, 0, 2, minus 2, 0. Now, what do you notice about the first and third rows? Well, they're the same up to a number, right? So they're multiples of each other. Which means if I, for example, multiply the first row by 2 and add to the bottom row, that would knock the bottom row out. So we get 0, minus 1, 1, 0, 1, 0, 0, 0, and 0, 0, 0, 0. And that's about as simple as we can get. I can't see anything that would really make something simpler that we can do. So let's read the equations. What's the first equation tell us about our entries? Yeah, so remember it's u1, u2, u3 going across. So 0u1 minus u2 plus u3 equals 0. The second equation tells us what? u1 equals 0. And so that says, hey, if I have an eigenvector u1, u2, u3, the first entry has to be 0, and the last two have to be the same. So anything of this form is an eigenvector, and all eigenvectors have this form. Well, how many eigenvectors do we have? Up to scalar multiple. We have 1. One eigenvector, which means, ha 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 ha, we're back here. We get to work our way up. Yes?
How do we know how many eigenvectors we have?
So you really should ask, how many choices do you get to make? So the answer is we get to make one choice. In this case, we called it U2. We could have called it U3. But the number of eigenvectors is the number of free choices that are available at the end of the process, after you've simplified as much as you can. So that's how we know how many we have. So that says that our solutions, so there's going to be 3 of them. The first one will look like e to the 3t times this vector u that we just found. The second one, so I'm just going to copy here, in case you're wondering where this is coming from. It will be e to the 3t times tu plus v. And the last one will be e to the 3t, 1/2 t squared u plus tv plus w. Where we have a minus lambda I times u equals 0. We've already found that one. A minus lambda I times v equals u, and a minus lambda I times w equals v. So we know u is 0, 1, 1. So that we have to find v, and we have to find w. All right. Well, yes? I'm copying x1, x2, x3. I'm just using u, v, and w instead of this v1, v2, v3. And where we have the relationships. All right. Where do we go next on our solution? Yeah, we should find v. Good idea. Right. You work your way up. You find u. After you find u, you found v. After you found v, you find w. All right. So I'm just going to make some notes here. We need a minus lambda I, which is here, times our v, v1, v2, v3, has to equal our u, 0, 1, 1. All right, so let's see what we have. Well, this should look familiar. It's a system of equations. Great. So let's write it in the way we would normally write systems of equations. And now what do we do?
Do the same stuff as before.
Yeah, it's like deja vu. It's like, ooh, yeah, this feels like very similar to before because it's very similar to before, yeah. So we say, hey, I like that middle row. So multiply the middle row by -2 and add to the top. Multiply the middle row by 3, add to the bottom. And we get 1, 0, 0, 1. And we'll get 0, minus 1, 1, minus 2. And 0, 2, minus 2, 4. Now what?
Two at the top to the bottom?
Yeah. Again, very deja vu-y. It's okay if you're like, but doesn't that feel like the same thing we did before? Isn't that a good thing? It's like recycling. We're good for the environment, mathematicians. Okay. It knocks out the whole bottom row. When you multiply the top row by 2 and add to the bottom. All right. Well, let's read these equations off. So you have V1, V2, V3. What does the first row tell us? Minus V2 plus V3 equals minus 2. What does the second row tell us? V1 equals 1. And the bottom row tells us 0 equals 0, which is okay. It's always true. Good. That one was satisfied automatically. Now, we have to find choices for V1, V2, V3 where these two equations are always true. So, anybody have some candidates for us? And there's usually lots of correct answers. Find an easy one. So V1 definitely has to be 1. No shock there. And what? Well, if this is negative 1, what does V3 have to be? I'm not saying that you can't choose negative 1. I'm just saying, what if, how about, try this on. How about 1, 2, 0? Right? Because if minus 2 is minus 2, and then that one is 0. So I like things with zeros. Zeros are our friend. We like zeros. Okay, so what's that tell us? Well, it tells us what V is. V is 1, 2, 0. Now, could we check our answer? Yeah, how can we check our answer? Yeah, we would multiply here by 1, 2, 0, and we'd see what we get. So we get 2 minus 2 plus 0, which is 0. That's good. 1 plus 0, which is 1. Minus 3 plus 4 plus 0, which is 1. So it works. Okay, so now we have V. Okay, what comes after finding V? Finding W. Great. Okay, so we're going to take our A minus lambda I. So again, I'm copying it down. 2 minus 1, 1. 1, 0, 0. Minus 3, 2, minus 2. And then we're multiplying it by our W1, W2, W3. And that has to equal 1, 2, 0. Okay. Well, set up our systems of equations. And let's see what happens. So what should we do? Yeah, same as before, right? So do you trust me to go a little bit quicker here? Yeah. Even if you don't trust me, I'm going to do it anyways. Because we only have a few minutes left, and we want to make the most of our few minutes. Okay, so multiply by negative 2 and add up. We'll get 0, minus 1, 1. And here it'll be minus 3. Middle row stays as 1, 0, 0, 2. Bottom, multiply by 3 and add down. We'll get 0, 2, minus 2. Then it'll be 6. Well, can we combine the first and last rows together in a nice way? Yeah, wow. Almost as if it was meant to happen, because it was meant to happen. So we get 0, minus 1, 1. Minus 3, 1, 0, 0, 2, 0, 0, 0, 0. So if we're thinking about these in terms of our equations for W1, W2, W3, the first equation says minus W2 plus W3 has to equal negative 3. The second equation says W1 has to equal 2. Can we think of a vector, or rather I should say, choices for W1, W2, W3 where we can satisfy that? We don't need to worry about the third equation. Okay, W1 has to be 2. Then what? 2, 3, 0. All right, I've convinced you. Zeros are your friend. Now, that says W is 2, 3, 0. Okay, and there is our 3 answers, and we combine them together. But give me one more second here. I want to point something out. You might be saying, wait, what if we are like, let's keep going? What do you think will happen? Could we get a fourth solution? So 2 minus 1, 1, 1, 0, 0, minus 3, 2, minus 2, I'll say x1, x2, x3 equals W 2, 3, 0. I just want to, it's fascinating to me what happens. And so we do what we did before, and you're like, this seems like the same as before, because it's like the same as before. We still multiply in the same way, we combine in the same way, and we say, okay, so we're getting 0, minus 1, 1, and then minus 4, 1, 0, 0, 3, downstairs, 0, 2, minus 2, and 9. And now, you multiply by 2 and add down, and we get 0, minus 1, 1, minus 4, 1, 0, 0, 3, 0, 0, 0, 1. What does this last equation tell you? That's very, very hard to satisfy. It's never satisfied. So that's why the machinery breaks down when it'll stop. And it breaks down at the right point. Have a good day.